task is to take a selection of 3D objects and efficiently pack them into a delivery box using a robotic arm. To do this, we must first design and build an autonomous system that can solve various technical challenges. How do we know when an item is ready to be packed, and what are the current contents of the delivery box? How do we use this information to determine the optimal position to place the item? How do we plan a safe trajectory from the item's current location to this desired end position? And what torques should be applied to each joint of the robot arm to perform this motion? There is also the challenge of simulating all the collisions that occur between objects, as well as coordinating when the different tasks should be performed.
The 3D subsystem consists of the robot, 2 conveyors, as well as the packing items themselves. The robot is called a doto robot, an industry standard whose clever design ensures that the end cannot rotate. By using only 3 motors, located in the base, we can move the end effector in the X, Y, or Z direction. The end is fitted with a vacuum that can apply a suction force to objects.
We use Simulink and MATLAB to connect everything together, marshalling the positions of the objects from the image processor into a format that C++ understands, and then transforming the output of the optimizer into the reference frame that the pick-and-place robot uses. This all forms one central loop of information, from the current positions of everything to the chosen position of the object to be packed, to the state of the pick-and-place robot, and back to the index of the next item.
The image processor subsystem takes information about the frames of each of the parts in the model and the container, alongside the position of a camera in the base of the Delta robot, and computes the relative position of each part with respect to the robot using a number of transform sensors. These part positions are then passed into function blocks, using a model ID signal to give the planning and control subsystem the position of the currently handled part, and using constants from the model workspace to calculate measures for the container and each part within it, passing those to the optimizer subsystem.
The process optimizer starts by scanning the items already in the box, recording the block space at each height. For each distinct 2D Boolean array of block space, we find the maximum empty rectangles. These correspond to cuboids of empty space. We now have a list of empty spaces in the box, which we can sort using a heuristic. We then pick the first empty space that can fit the item and has a stable position that the manipulator arm can reach. We then place the item there.
In the planning phase, we have to ensure that the item actually ends up in the box, and this is the part where most things go wrong. A trick is to find a good intermediate position so that the robot can always freely move to and from it without collision. In the control phase, we use math to convert robot torques to gripper coordinates, interpolate them with the desired position, and then use math again to convert resulting coordinates back to torques.
We use MATLAB state flow to model and simulate decision logic using state machines and flowcharts. The logic block implements a design that develops the supervisory control and task scheduling. Here we have a representation of events and how the model reacts to the input signals. All 4 state charts run in parallel and are interconnected through events that trigger actions from one state to another. The state machine control variant implements the supervisory logic for the entire system, the robot arm, and both conveyor belts. Information from sensors in the model come in as input signals. By using active state data as output from the state chart, we represent the current active state during the simulation, which will trigger the movement of the robot and the belts. For example, signaling whether the conveyors are in the move or wait modes.